I'm Rajesh Uppal, Director IDST. We bring sharp insights and foresight on defense, security, and emerging tech. Let's dive in.
Imagine looking out at the night sky and realizing that everything you see, the stars, galaxies, planets, even you and me, makes up less than 5% of the universe. The rest, scientists say, is made of something invisible. It doesn't glow, reflect, or absorb light, yet its gravity shapes the very structure of the cosmos. This mysterious substance is called dark matter, and it outweighs ordinary matter by nearly 6 to 1. We know dark matter exists not because we can see it, but because of what it does. Galaxies spin faster than they should if only visible matter were present. Massive galaxy clusters bend light from objects behind them, a phenomenon called gravitational lensing, revealing extra mass we can't see. Even the early universe, as captured in the faint radiation known as the cosmic microwave background, carries its imprint. So dark matter is real, but we have yet to find a single particle of it directly. So why is it so hard to detect? Unlike ordinary matter, dark matter doesn't interact with light or with the electromagnetic force at all. It doesn't emit or reflect light, nor does it collide with normal atoms in any noticeable way. The only force it seems to obey is gravity, and possibly the weak nuclear force, one of the fundamental forces responsible for radioactive decay. Because those interactions are so faint, dark matter slips right through us, the Earth, and even the most sensitive detectors without leaving a trace. Scientists have proposed several ideas for what dark matter might be made of. One leading candidate is called a WIMP, short for Weakly Interacting Massive Particle. These are heavy particles that might occasionally bump into normal atoms, but so rarely that catching one would be like winning a cosmic lottery. Another candidate is the axion, a hypothetical ultra-light particle that could behave more like a wave than a particle. And there are other possibilities too, like sterile neutrinos or even tiny black holes left over from the early universe. So, how do we even try to detect something so ghostly? Researchers have come up with 3 main strategies, each one approaching the mystery from a different angle. The first is called direct detection, literally trying to catch dark matter particles hitting regular atoms. To do this, scientists build enormous detectors deep underground where the Earth's crust shields them from cosmic rays and other interference. Inside these detectors are massive tanks filled with liquid xenon or argon, cooled to cryogenic temperatures. That's hundreds of degrees below zero. If a dark matter particle were to strike one of those atoms, it might release a tiny flash of light and a few free electrons. Experiments like XENONnT in Italy, LUX-ZEPLIN in South Dakota, and PandaX in China are all listening for these rare, delicate signals, sometimes expecting no more than a single event per year per ton of detector material. The second strategy is indirect detection. Instead of trying to catch dark matter itself, scientists look for what might happen when dark matter particles interact with one another. Some theories suggest that when 2 dark matter particles collide, they could annihilate each other and produce detectable radiation, such as gamma rays, neutrinos, or positrons. Telescopes like NASA's Fermi Gamma Ray Space Telescope and the Alpha Magnetic Spectrometer aboard the International Space Station are scanning the skies for these possible byproducts. The third approach takes place in giant particle accelerators, most famously the Large Hadron Collider at CERN in Switzerland. Here, scientists smash ordinary particles together at nearly the speed of light, hoping the collision energy might create dark matter particles. The dark matter itself would pass through the detectors unnoticed, But scientists look for missing energy or momentum, tiny imbalances that could hint something invisible was created and flew off. After decades of experiments, no one has yet detected dark matter directly, but every result teaches us something valuable. It narrows down the possibilities, guiding us toward where to look next. And that next step might come from an unexpected direction, the strange and delicate world of quantum physics. In July 2024, scientists from several UK universities announced 2 revolutionary experiments that combine the principles of quantum mechanics with the hunt for dark matter. These detectors are cooled to just 1,000th of a degree above absolute zero, the coldest temperature possible, where almost all atomic motion stops. Why go so cold? Because heat creates noise, and in these ultra-sensitive instruments, even the tiniest vibration could drown out the signal they're looking for. By removing that noise, the detectors can listen for the faintest whispers of dark matter passing through. One of the new systems targets axions. These particles are theorized to occasionally turn into photons, particles of light, when they move through strong magnetic fields. The experiment uses superconducting circuits and microwave resonators, similar to those used in quantum computers, to try to detect this transformation. Imagine tuning a cosmic radio to a frequency so sensitive it could pick up the faint hum of a particle no one has ever seen. The second experiment is aimed at detecting WIMPs, using quantum-entangled qubits, the same kind of building blocks used in quantum computing. When qubits are entangled, they can sense and amplify incredibly small disturbances together. These detectors can measure energy changes as tiny as a zeptojoule. That's a trillionth of a billionth of a billionth of a joule. Small enough to catch even the gentlest nudge of a dark matter particle. Other experimental concepts are also emerging. Some use superfluid helium, a form of matter that flows without resistance at near zero temperatures, to detect quantum ripples caused by passing dark matter. Others employ squeezed light states, a quantum trick that reduces measurement uncertainty below the normal limit, allowing scientists to spot impossibly faint signals that would otherwise disappear in noise. These quantum experiments represent a new era in dark matter research. They combine precision engineering, cryogenics, and quantum sensing to create instruments so sensitive they can detect changes at the edge of physical possibility. Over the next few years, scientists aim to scale these detectors up to kilogram-sized systems while maintaining their extraordinary sensitivity. If successful, they may finally give us the first direct glimpse of dark matter, or perhaps reveal something even stranger, forcing us to rewrite parts of physics itself. The stakes couldn't be higher. Detecting dark matter would not only solve one of the greatest mysteries in modern science, but could also open new windows into the fundamental nature of reality. It might uncover hidden forces, new dimensions, or unknown particles that reshape how we understand space, time, and matter. For now, the search continues, colder, quieter, and more precise than ever. Every photon, every atom, and every qubit in these detectors brings us closer to solving the mystery of the invisible universe. In a cosmos where most of what exists cannot be seen, the quest to find dark matter is ultimately a quest to understand ourselves and what the universe is truly made of. Thanks for watching. Subscribe, follow, or visit idsth.com for more cutting-edge defense and tech insights. See you in the next one.